Chapter 21, Molecular Orbital Theory, Section 21.5, Heteronuclear Diatomic Molecules. The MO diagram of lithium hydride is similar to the MO diagram of H2. The lithium 2s atomic orbital interacts with the hydrogen 1s atomic orbital and form a 2 sigma bonding orbital and a 3 sigma star anti-bonding orbital. There is no G or U symmetry in this heteronuclear diatomic molecule because this molecule does not have any center of symmetry. The lithium 1s orbital has significantly lower energy than the hydrogen 1s orbital, and therefore there is no interaction between this 1s orbital and this 1s orbital. The bond order of lithium hydride is 1. So we have this 2 bonding electrons, 0 anti-bonding electrons. The difference is 2. 2 divided by 2, that's 1. Over here, although it's written as 1 sigma, however, it's not really a bonding orbital. This 1 sigma is awfully similar to this just 1s orbital because, again, the interaction between the lithium 1s orbital and hydrogen 1s orbital is negligible. The ionization energy of lithium is 0.2 atomic unit. The ionization energy of hydrogen is 0.5. Therefore, the lithium 2s atomic orbital lies above the hydrogen 1s orbital. This atomic orbital energy is negative 0.2. This atomic orbital energy is negative 0.5. So the ionization energy is simply the amount of energy to promote this electron from negative 0.2 to 0. The difference is 0.2. The ionization energy for hydrogen is the amount of energy required to promote this electron from negative 0.5 atomic unit to 0. Therefore, the ionization energy of hydrogen is 0.5. So now we place the lithium 2s orbital above the hydrogen 1s orbital. And these two may form 2 sigma and 3 sigma star, bonding orbital, anti-bonding orbital. There is no G or U symmetry. And over here, because this sigma is the bonding orbital, and this 1s orbital has lower energy than the 2s orbital. This 2 sigma is closer to the hydrogen 1s orbital than to the lithium 2s orbital. And that means in this 2 sigma, it contains more than 50% of hydrogen 1s, less than 50% lithium 2s. However, if you look at this 3 sigma star anti-bonding orbital, it contains more than 50% of the lithium 2s, less than 50% of hydrogen 1s. Note that the ionization energy is the absolute value of the energy of the highest occupied atomic orbital, HOAO. So when you see this atomic orbital energy over here, well, the ionization energy is positive 0.5. When you see this energy of HOAO of lithium is negative 0.2, then the ionization energy is positive 0.2 AU. The energy of the highest occupied atomic orbital of a neutral atom is always negative, such as negative 0.5 for hydrogen 1s, negative 0.2 for lithium 2s. The ionization energy of a neutral atom is always positive. It always takes some energy to promote an electron from the highest occupied atomic orbital in an atom to an energy of 0. The MO diagram of hydrogen fluoride shows that the fluorine 2pz atomic orbital interacts with the hydrogen 1s atomic orbital and form a 3 sigma bonding orbital and 4 sigma star anti-bonding orbital here and here. The other 2 p orbitals do not interact with the hydrogen atomic orbital. So we just shift this to here at the same energy level. However, for just naming purposes, we now call them 1p orbitals and 1p electrons, but really those are just the 2px and 2py electrons in 2px, 2py orbitals. It's just in the MO diagram we have a different name for these electrons. Now let's look at the bond order. We have 2 bonding electrons in the 3 sigma bonding orbital. 0 anti-bonding electron here. So 2 minus 0 over 2, that's 1. The bond order of hydrogen fluoride is 1. What about these 4 electrons? Again, although they are labeled as 1p electrons, they are neither bonding electrons nor anti-bonding electrons. These 4 electrons are still the 2px and 2py electrons on fluorine. What about the 2s orbital of fluorine? Well, the 2s orbital lies far below the hydrogen 1s orbital. So even if there's some interaction between the fluorine 2s orbital and hydrogen 1s orbital, the interaction is negligible. So we just have this 2 sigma here with the same level as this 2s, and these 2 electrons are not considered bonding electrons, because these 2 electrons essentially are just the 2s electrons of fluorine. The highest occupied atomic orbital energy for fluorine is negative 0.64. So I drew this 3 lines lower than the hydrogen 1s orbital, negative 0.5. Now when this and this form a 3 sigma MO, this MO, because this energy level is closer to this one, this 3 sigma contains more 2pz orbital of fluorine than this hydrogen 1s orbital. Now if we look at this 4 sigma star, it contains more than 50% of hydrogen 1s and less than 50% of fluorine 2pz. So again, because this 3 sigma contains more than half from this fluorine 2pz, you can see these 2 shared electrons are closer to the fluorine atom, because there is more than 50% probability of viewing these 2 electrons in the 2pz orbital of fluorine. And that is something we have learned in general chemistry. When you form a hydrogen fluorine bond, the electrons are closer, the shared electrons are closer to the fluorine atom than to the hydrogen atom.